All right, so we're back looking at L-Trominoes again. So an L-Tromino is this shape formed by joining three unit squares along their edges to form an L shape. So you end up with this sort of situation. All of these shapes are considered the same shape, obviously. Last video on this topic, we spoke about these first four questions, so I strongly recommend you go and have a look at that. I'll put a link below. But what we're going to talk about today, we sort of left this because we just needed to break it up. But the last two questions are, well, what about a 50 by 50 chessboard? And what about a general n by n for n not a multiple of 3 chessboard? So I don't know, something like 19 by 19, how might we work that out? Basically what we're going to do, as I've explored this world a bit, I think the best way to explain it is to go with a general n by n first, where n is odd and not a multiple of 3. And then actually in another video, we're going to come back and we're going to finally look at a 50 by 50. So it might be a bit frustrating, but yeah, it actually gets quite complex. So hopefully you come along for the ride. If you are finding these videos interesting, they're hard work to make. I do enjoy making them, but they take a lot of effort and I obviously don't get paid for doing it. So if you could just like or subscribe, I think that would be great to sort of share your engagement with maths and hopefully find it a bit interesting or learn something new. So also I have a Patreon. Apparently you can support me financially through Patreon, or you can do it for free. So who knows, maybe that's how we keep this going. All right, essentially what we're going to talk about today is a paper that was published in 1986 by Chu and Johnsonbaugh. Now, I'm sure I got those names incorrect, but basically throughout this video, we're going to be looking at n by n boards where n is odd and n is not divisible by 3. And we're going to start like at 7 and work our way up. Actually, we'll start at 5 because that's going to be important for our proof of this theorem. And the theorem says this: if n is odd, greater than 5 and not divisible by 3, then any deficient n by n board can be tiled with L-Trominoes. Okay, just that term deficient, meaning you can tile the whole thing except one square. Yeah, and that's what that means. And essentially our video is just going to talk about this theorem and building up to that theorem. So yeah, if it's an n by n, then there's n squared squares in the board, and then so we take away one square. It's gives us exactly L Trominoes. N squared minus 1 on 3 would be the number of Trominoes you need to tile an n squared minus 1 sized area chessboard, I believe. Okay, so here are the propositions we need to understand before we can actually prove that theorem. The first is this: we need to look at a 5 by 5. Essentially, a 5 by 5 can be tiled with one corner removed, and that's going to be important. Proposition 2, we're going to look at rectangles. Proposition 3, we're going to look at deficient 7 by 7 boards. And then the theorem is obviously what we're trying to prove based on these propositions. And hopefully, it'll all come together at the end. So let's have a look at this, a 5 by 5 board. Okay, and I've put a link below for a paper that explores this in more detail. But basically, just by construction, we've literally just made it here. We've got our L-Trominoes. We can see that we can have the corner removed. And that means obviously through rotation, any of the corners could be removed, right? That's important for our proof of the theorem. And so just keep that in mind. That's proposition 1. You can have a 5 by 5 with the corner removed. If you want to know more about 5 by 5s, essentially, yeah, you can have other squares other than the corner removed, but I'll leave that to you to go and research. It's not too hard to understand which positions can actually be removed. Not all positions. A 5 by 5 doesn't work. You can't tile it such that every square is missing, I suppose is what I'm trying to say. It's only certain squares that can be missing, but the corner is one of them, and that's all that we need to know for our induction that we're going to do later on. So that's proposition 1. Proposition 2, rectangles can be tiled completely. And I think this is the most straightforward part of the video. So if you've got one brick, if you put two Trominoes together, you get a 2 by 3 brick. And so you can see just by that logic, any multiple of 2i by 3j rectangle can be tiled completely. So if the number of rows you have is a multiple of 2 and the number of columns is a multiple of 3 or vice versa, then you can tile that rectangle completely. So it's not that it's deficient. Deficient would mean it's missing one square. It can be tiled completely. And so that's proposition 2, which will be useful in a moment. Okay, proposition 3. Every deficient 7x7 board tiles, and again that means that the missing square can be anywhere. So here's an example where the missing with the 7x7 where the center is missing. So obviously I'll just, if you just want to get comfortable with the count, 7 squared minus 1 is 48. So we're using 16 L-Trominoes here, and we've got the center cell missing, and we've got we've got the center cell missing there. We can also do it with the corner cell missing. So here's another valid tiling where the corner cell is missing. Again, I'll leave it as an exercise up to you to sort of go and look at that paper. I can put a link below to the paper, but if you want to reach out and access that paper, just let me know and we can discuss some things. But basically, when you've got this 7x7, it breaks up into a 5x5 deficient subboard in the corner, and then you can tile the remaining rectangles. But yeah, what we need to know is that a 7x7 can be done with any position in that 7x7 being removed. And that's going to be important for this very last step, importantly, which is the theorem. So for an odd number greater than 5 and not divisible by 3, you can tile the chessboard. So let's look at n equals 11. This is going to be sort of our base case. 7 is kind of like the base case as well, but we've got 2 base cases. And here, I think, is where we need to, this is sort of the big idea. So we've got 11 by 11. We're going to say, just by rotation, that the missing square S is in this top left-hand corner. It's inside a 7x7. So I've broken it up into these 4 different areas. So we've got a 7x7 here with the missing square. We know that the missing square can be anywhere inside that 7x7 just by that proposition 3 that we just spoke about. So that leaves us with so this length here is 7 obviously, this length here is 4, so that gives us a length of 11. But we know that this is a 6x4, and that's a multiple of 2 and 3. So we know by proposition 2 that the 6x4 and the 4x6 can be tiled completely. Okay. We also know by proposition 1 that the 5x5 can be tiled deficiently, so there can be 1 square missing. Okay, but now this is where I think it came together for me in terms of understanding. There's a missing square up here somewhere, and so let's just assume the missing square is somewhere up here. This one is filled in by the 7x7 then, because the missing square is over here, right? And so the deficient 5x5 can be tiled, right? We know that everything else except this point can be tiled by the 5x5 because we know that 5x5 can have the corner removed. So we can tile this whole thing, we can tile this 11 by 11 just using that logic, because this can be done, this can be done, this is deficient and this is deficient. So there's 1 square missing overall. And so I think that's, really fascinating. And then the last thing that we're going to do, which is to prove this theorem now, is do proof by induction. So just a very quick reminder about proof by induction. It basically says you've got this ladder that goes up to infinity. If you can get your first foot on the ladder, which is to prove the base case, which we did for 7 and 11, let's call it 11. So we've proven the base case. We need to prove that we can get to the next step on the ladder. And then if we can get to it from the base case to the first step, that means we can get to every step on the ladder from there. That's essentially what proof by induction does. A very powerful technique. And so this is where it gets tricky. Our inductive step is to rotate it so that in the top left, we have an n-6 by n-6 subboard. So let's have a look what that looks like. And you're probably screaming and wondering why on earth, what the hell does this have to do with the number 6? But this is what we'll end up with, and I'll explain. And I'm actually just going to put the steps there as well. Okay. So our induction is this. We're saying that an n-6 by n-6 can be, this is sort of our, this is our inductive step. We're saying that an n-6 by n-6 can be tiled deficiently. And so this one can be tiled deficiently. We're going to be left with a 7 by 7 here. We're going to be left with a multiple of 2 and 3 in our rectangles here. And you probably, again, just with the n-6 situation, the reason we're doing that is because if n is greater than 5 and odd, and not divisible by 3, then n minus 6 is odd. It's not divisible by 3, and it's greater than 5. I think this is where it got confusing for me. Why have we got n minus 6? But it's for those conditions. So let's just take 19. 19 is n. So let's just imagine this is 19. Actually, let's take 13. That would be the next one along, wouldn't it? 13 would be the next one along. So this is 13 by 13. So n minus 6 would give us a 7 by 7. Well, we know that that's deficient. We can tile that with 1 square removed. Then we would have a 7 by 7 down here. That's always a 7 by 7. That would make this a 6 by 13 minus 7, which is 6. So this would be a 6 by 6, and this would be a 6 by 6. Now, it might be a little bit confusing because these would be squares. These would all be squares, but there's no rule against that. 6 and 6. 6 is a multiple of 2 and 3. So proposition 2 holds for that. And so essentially, you end up in this situation where you can have, by that induction, you can show that 13 would work as well, because that that induction holds. And so we can say that it's tileable by the inductive hypothesis based on these hypotheses, based on these propositions rather. So every deficient n by n board where n is greater than 5 and not divisible by 3 can be tiled. Okay, I just want to really step it out again. So let's just think if n was 19, if you had 19 by 19, then up here you would have a 13 by 13, and then you'd have a 7 by 7, and then you'd have a 6 by 12. I think I got that right. And that would all be tileable based on the propositions that we've outlined. So I think that's interesting. And you're probably screaming as well because you want to know what about a 50 by 50, but that's a situation where n is even. So I will come back later on at some point and talk about n being even. But at the moment, we just look at n being odd, but very similar logic, I think, for proving why n is even. Essentially what I've done here, guys, is I've just hopefully made it a bit more user-friendly, a paper that I'll put a link to below. Hopefully you found that interesting. If you did, give us a thumbs up. Looking forward to hearing what you think about it. And talk to you soon, and good luck with all your mathematics studies.